Okay, so we got here question 4.1. This question is about elements in the periodic table. What order did scientists use to arrange the elements in the early periodic table? Now, the only answer that you will need for this is atomic weight. That is as simple as that. Is just the fact that you need to remember, okay? Question 4.2. In the early periodic table, some elements were placed in wrong groups. Mendeleev overcame this in his periodic table. Give one way that Mendeleev did this, right? So there are a couple things here. You could say that he left gaps or spaces for elements that were yet not discovered. She changed the order based on atomic weight. And you could say that he placed some of the elements in the groups according to their properties, but you wouldn't get any marks for saying that anything that had to do with the atomic number, okay? So let's write those down. Okay, so there you have it. Let's go to question 4.3. Table 2 shows the boiling points of fluorine, chlorine, and bromine. So that's your table 2, the elements fluorine, chlorine, and bromine, and the boiling points are there. Explain why the boiling points in table 2 are low. Okay, now the boiling point is that temperature in which a substance becomes a gas. Now, bromine is plus 56 degrees Celsius. If you consider water, which is 100, that is pretty low. And then we're looking at chlorine at minus 34 degrees Celsius. That is pretty cold for a human, but for chlorine, that is the temperature that it actually becomes a gas. And then you got fluorine at a ridiculous 186 degrees. Fluorine at 186 degrees becomes a gas. Anything lower than that, it will turn into a liquid, okay? Right, so explain why the boiling points in table 2 are low. Now, the very first thing you gotta remember is that these substances are non-metals. Okay, they're non-metals. And if you think about the formula for fluorine gas, that's going to be F2, chlorine gas, that's going to be Cl2, and then bromine, which is going to be Br2, okay? Now, what these two tells us is that fluorine is made of only 2 atoms, chlorine is only made of 2 atoms, and bromine is only made of 2 atoms. And if they are only made of a few atoms, they are not going to be giant covalent molecules, they are going to be simple covalent molecules. And the thing with simple covalent molecules is that they have very weak intermolecular forces between the molecules, which require very little energy to overcome and break apart, okay? And that is your 2 marks right there. Now, I'm gonna explain this very quickly here. So if you have a fluorine, okay, that's a fluorine joined with another fluorine, that there in the middle is going to be a covalent bond. And if I have another fluorine and another fluorine in between those 2 atoms, there's going to be covalent bonds. But in between the molecules represented by those lines, you don't have covalent bonding. That is what we call intermolecular forces. And those intermolecular forces right there are very, very weak, which require very little energy to break apart, making those molecules fly away from each other, turning into gases, okay? So your 2 marks would be that those molecules of those elements have very weak intermolecular forces, that very little energy is required to break them apart. And that is all you gotta do. You don't have to say anything about the covalent bonds. You just need to talk about the intermolecular forces. So let's write that down. All right, there we have it. Now, question 4.4. Explain the trend in the boiling points in table 2. Now, we have explained why those temperatures are very low for them to become gases, but now we need to explain the trend. Now, when we look at the periodic table, fluorine is at the top in row number 2 or period number 2. Then you have chlorine in number 3, and then you have bromine in number 4. Now, what this is telling me is that as you go down the group, the number of shells increase. Therefore, the atoms are getting bigger. Now, when it comes to intermolecular forces, the bigger the molecules, the stronger those intermolecular forces are going to be. Now, they're not going to be as strong as ionic bonding or covalent bonding, but certainly intermolecular forces from a small molecule are going to be weaker than the intermolecular forces from a bigger molecule, okay? And that is the reason why, as you're going down the group, because the atoms get bigger, those intermolecular forces also get stronger. Therefore, they need more energy to be broken apart and separate those molecules from each other. So let's write this down. Okay, now notice that I have underlined forces between molecules increase, okay? That in the mark scheme is underlined, which means that it is absolutely necessary for you to have written that down in order for you to get those full 3 marks, okay? And this is what I keep on saying, you need to make sure you look at mark schemes to ensure that you understand the language that is required from you in an AQA paper, okay? Okay, question 4.5. Explain why neon is unreactive. Give the electron structure of neon in your answer. So you have 2 marks over here. Why is unreactive? 2, give the electronic structure. Okay, you need to mention both of them in order to get the full marks. So let's write that down. Okay, so first of all, neon is unreactive because it has a full outer shell. It has a complete outer shell. It has a stable configuration. Okay, that is the reason why. And then for the electronic configuration, you would write down 2, 8, which means it has 2 electrons in the first shell, 8 electrons in the second shell. So let's write those down. One thing I want to point out here is that very often what you students tend to do, and I used to do as well, is that when it says explain, you're going to start saying the reason why neon is unreactive, and that there is irrelevant, is a waste of time. So every time you see the word explain as your command word, your answer should start with because, okay? And it stops you from diverting your answer to something else as you're trying to embellish your answer. It's just straight to the point in science, okay? So explain why neon is unreactive because okay, so there you have it. Question number 6.4. How many atoms are there in 1 gram of argon? The Avogadro's constant is 6.02 times 10 to the power of 23 per mole, and the relative atomic mass of argon is 40. Okay, now this question very often gets just neglected. Okay, a lot of people tend to just not answer the question or start multiplying random things, but we need to understand what this actually means. Now, Avogadro's constant 6.02 times 10 to the power of 23 per mole means that there are that many atoms of a specific element in the number of grams that that element has that matches its atomic number. So for instance, the atomic number of carbon is 12. If I had 12 grams of carbon, okay, in those 12 grams of carbon, there's gonna be 6.02 times 10 to the power of 23 carbon atoms, okay? That's what that means. If I had magnesium, magnesium is the atomic number of magnesium is 24. If I had 24 grams of magnesium, I would have 6.02 times 10 to the power 23 atoms of magnesium in those 24 grams, okay? If I had only 12 grams of magnesium, I would have half of that, okay? Now this number is called a mole. So if I only had 12 grams of magnesium, I will have half a mole. If I have 24 grams of magnesium, I'll have 1 mole. So in this case, we have argon, which is the relative atomic mass is 40. So that's going to be the relative atomic mass. Okay, that's going to be the 40. So which means that if I had 40 grams of argon, in there is going to be 6.02 times 10 to the power of 23 atoms. Okay, that is there how many atoms, okay, I'm gonna have if I have 40 grams of argon. But this question is saying how many, so 1 gram of argon, how many atoms would I have there? So all you're doing is that you're getting those 6.02 times 10 to the power of 23 atoms, you're dividing it by 40, okay, and whatever you get means that that is what you're going to have in just 1 gram of them. Okay, 6.02 times 10 to the power of 23 divided by 40, and that is going to equal 0.0. Okay, there we go, and that is going to be your answer because you have divided that in 40 equal sections. So that's 40, each one of those equal sections is 1. That is how much each one of those 1 grams is going to have, and if you add them all together to make 40 grams, this is how many atoms it's going to have altogether. Okay, so your answer would be 1.505 times 10 to the power of 22. Now it's not asking me to do any significant figures or decimal places, so it's okay to just leave your answer like that, and that's gonna be your full 2 marks in that question. Okay, so that is the end of question number 4. So click on the next video so we can look at question number 5. Right, so there you have it, quick time revision. Like and subscribe, and I'll see you next time.